Imagine standing beneath a towering wind turbine, its giant blades slicing through the air to generate clean electricity. What you might not realize is that deep inside the turbine's generator, an element is hard at work. That element is samarium, a rare earth metal playing a critical role in making wind power possible. Samarium isn't a household name. It doesn't shine brightly as gold or spark curiosity like uranium, but it has some extraordinary properties and uses. In fact, this silvery gray metal is one of the quiet heroes enabling modern technology, from high-performance magnets in wind turbines to cancer treatments and beyond. Welcome to Cube Chemistry, where we will discuss all the elements of the periodic table and also do experiments. Now, if you like this video and want to see more, make sure to like, subscribe and hit the notification bell so you will never have to miss another episode. Also, make sure to fill out the poll in the post section of the channel for next week, as we will be doing another experiment. Now, since you guys keep selecting the lanthanides in the poll, I hope you did not expect a beautiful colored element in the cube, since lanthanides are kind of all the same silvery gray. So also this one. Although these seem to be more brittle than lutetium of last week. Well, this one is called samarium. But as you are looking at this cube, you are probably thinking about one thing. Can I lick it? Well, using the periodic table, which, as we mentioned, will be rewritten at some point in the future, it states, go for it. But I disagree in this case with the table here. Pure samarium is highly reactive, especially with air and moisture. If you exposed a fresh piece to open air, it would quickly form samarium oxide on the surface. Now, that oxide is a dull, crusty layer, not pleasant to touch, let alone to put in your mouth. And under the right conditions, samarium can even ignite in air if heated. It could react to the moisture in your mouth, not explosively, but enough to irritate or cause chemical reactions. You don't want that happening on your tongue. So, I would rather place it in the yellow category. Maybe not a good idea. Now, if you want to collect samarium or one of the others like we do, click on the link in the description, use the promo code, get a 10% discount, and you will also be helping out our channel. In the 19th century, an era when chemists were avidly hunting for new elements, samarium was first identified in 1879 by a French chemist named Paul-Émile Lecoq de Bosbourgin. He was examining a heavy black mineral called samarskite, which has been found in the Ural Mountains of Russia. By carefully isolating the constituents of samarskite, Bosbourgin detected a new substance with distinct spectral lines, basically a unique fingerprint of light, indicating the presence of a new element. He had discovered samarium, atomic number 62 on the periodic table. Bosbourgin decided to name this new element samarium, after the mineral samarskite. And samarskite itself was named in honor of a Russian mining official, Colonel Vasily Samirsky-Bykovets. In doing so, samarium earned a special distinction. It became the first element ever to be named after a person. Colonel Samarsky wasn't a chemist or the discoverer, but its name lives on through the mineral and the element. This indirect naming was a thank you gesture, since Samarsky had granted scientists access to the mineral samples from his mines, one of which turned out to contain the new element. Thus, samarium's very name is a little piece of history, connecting a Russian nobleman and a French chemist across continents. Now, it's worth noting that early on, isolating pure samarium was tricky. When Bosbourgin first found it, he had it in the form of samarium oxide mixed with other substances. In fact, what he had was not completely pure. It contained another new element, europium, which wasn't separated out until later. Over the next few decades, chemists refined their techniques, and by 1901, pure samarium oxide was finally prepared by Eugène Anatole de Marseille. And a couple of years later, in 1903, the metallic samarium itself was isolated by Wilhelm Muthmann. Now, before these pure samples were available, there was even some confusion. In 1878, a Swiss chemist announced an element called dicipium from similar minerals, which later turned out to be a mixture of samarium and other rare earths. The late 1800s were a bit of a puzzle hunt with rare earth elements, and samarium was one of the pieces that eventually fell into place. So, what is samarium like? Well, it's a metallic element. In pure form, it's a silvery white metal with moderate hardness. If you held a piece of samarium, it would feel firm, but not as hard as steel. Its density is about 7.5 grams per cubic centimeter, similar to metals like zinc. You know, zinc, that element in the pole that people refuse to choose to make an episode about. Now, freshly polished samarium can gleam with a silvery luster, but you probably wouldn't see that shine for long because samarium has the tendency to tarnish in air. In fact, it slowly oxidizes, reacts with oxygen, just sitting out at room temperature. Over time, an unprotected samarium surface will get a dull grayish-yellow film of oxide. This means that pure samarium has to be stored carefully, often under mineral oil or sealed in a container, to keep air and moisture away. Even then, it's so reactive that it will still oxidize gradually. And here's another startling fact. If you heat samarium in air, about 150 degrees Celsius or 302 degrees Fahrenheit, it will ignite and start burning with a bright flame. Now that tells you that samarium is quite reactive. It loves to form compounds with oxygen. It's not the type of metal that you'd make everyday objects out, because it would not stay shiny and it could even catch fire at moderate high temperatures. This reactivity is common among the rare earth metals, the lanthanide series to which samarium belongs. They are all quite eager to combine with oxygen, water, and other elements, which is why we don't often find chunks of pure samarium in nature. Chemically, samarium behaves like the typical lanthanide. In most of its compounds, samarium has an oxidation state of +3, meaning it gives up 3 electrons which form chemical bonds similar to its cousins europium and gadolinium. For example, the oxide that forms on it is samarium 3 oxide. But samarium is also a bit special because it can sometimes take up a +2 oxidation state in certain compounds. Samarium 2 compounds with samarium giving up only 2 electrons are less common, but they do exist. One notable example is samarium 2 iodide, a deep green crystal that chemists find very useful. More on that later. The ability to have 2 different oxidation states, +2 and +3, is somewhat unusual in the lanthanide series. Most lanthanides are almost exclusively +3 in compounds. This versatility hints that samarium has some interesting chemistry. In terms of atomic structure, samarium atoms contain 62 protons in the nucleus and a bunch of electrons arranged in a way typically for lanthanides, with electrons filling the 4f orbital. Now, without diving too deep into the quantum chemistry, what this means is that samarium electrons can align in certain ways that give it a particularly magnet and optical properties. Speaking of magnetism, you might assume samarium metal itself is strongly magnetic, since we hear about samarium magnets. But surprisingly, pure samarium metal is not ferromagnetic at room temperature. In fact, at room temperature, it's paramagnetic, which means that it's only weakly attracted by magnets and it doesn't maintain magnetization on its own. Unlike iron, for example, which is ferromagnetic and can make a permanent magnet. Now, if you cool samarium way down near absolute zero, around 14 Kelvin, which is about -259 degrees Celsius, it transitions into an anti-ferromagnetic state, a kind of magnetism where atomic magnets cancel each other out in pairs. These are very cool scientific details, but the key takeaway is that samarium's amazing magnetic applications come not from the pure metal by itself, but when samarium is combined in alloys or compounds. We'll soon talk about samarium cobalt magnets, which are the real stars. Now, in terms of physical properties, samarium has a melting point of about 1072 degrees Celsius or 1962 degrees Fahrenheit, and a very high boiling point of around 1794 degrees Celsius and almost 3260 degrees Fahrenheit. Interestingly, along the lanthanide, samarium is one of the more volatile ones, meaning it can evaporate at high temperatures more readily than many of its neighbors. Now, this fact is actually useful when chemists need to separate samarium from other rare earth elements. Heating a mixture can help samarium come out first due to its relatively low boiling point. Now, samarium metal will form different crystal structures depending on temperature and pressure. It can have several solid forms, from a rhombohedral arrangement of atoms at room temperature to different structures if heated and pressurized. But those details get fairly technical. Now, given samarium's reactivity, it's no surprise that we don't find pure samarium nuggets in the ground. Instead, samarium is always locked away inside minerals and ores. It belongs to the family of rare earth elements, which, despite its name, are not truly rare. in terms of abundance. In fact, samarium is more plentiful in the Earth's crust than some well-known metals like silver or gold. Estimates put samarium around 7 parts per million in the crust, making it roughly the 40th most abundant element. So why are they called rare earths? The term rare earth actually comes from the historical difficulty in isolating these elements, as well as the fact that they typically occur dispersed in ore and not in rich concentrated seams like iron or copper. Their earths, in the old chemical sense of earth meaning oxide, the first discovered rare earths were found in oxides. Samarium is usually scattered in small amounts within certain types of minerals rather than forming its own rich ore. The typical minerals containing samarium are also host to many other rare earth elements. Some of the important ones include monazite, which we also discussed last week, a phosphate mineral, and bastanaazite, a fluoride carbonate mineral. These two have been major commercial sources of rare earth, samarium included. Now, for instance, monazite can contain a few percent of samarium, along with other elements like cerium, neodymium, and others. Other minerals like cerite, gadolonite, and xenotime, and namesake samarskite, also contain samarium. Now, samarskite, the mineral that gave samarium its name, is a complex oxide containing elements like yttrium, uranium, iron, and rare earths including samarium. However, samarskite itself isn't mined on a large scale for rare earths today. Instead, monazite and bastanaazite have been the two workhorses of rare earth production. Now, geographically, where can we find samarium? Well, rare earth deposits are found in various parts of the world. Historically significant rare earth mining has happened in places like Mountain Pass, California, and the Bayan Obo region in China. Now, in the present day, China is by far the largest producer of rare earth elements, including samarium. By some estimates, China has been responsible for over 80% of the world's rare earth supply in recent decades. Other countries with notable rare earth resources include the United States, though production was paused and restarted at Mountain Pass, Australia with the Mount Weld mine, India, Brazil, and a few others like Vietnam and Russia. Samarium often isn't reported separately in mining statistics because it's usually extracted as part of a mixed rare earth oxide product. For example, a rare earth mine will put out ore containing a blend of lanthanides, and only after complex processing do we get individual elements like samarium separated out. World reserves of samarium as part of rare earth reserves are quite large, millions of tons in oxide form. But remember, it's all about extraction, difficulty, and economics. Extracting samarium from these ores is a chemistry-intensive process. Early on, mid-20th century, chemists used methods like repeated fractal crystallization to slowly tease apart these rare earths, a very laborious task. Nowadays, two main methods are used: ion exchange and solvent extraction. These techniques exploit slight differences in how rare earth elements stick to certain substances or solvents. Now, we've discussed this in a previous video, so make sure to watch it if you want to know more about that process. Now, to get metallic samarium from the oxide, a common method is to reduce it at a high temperature. One way is by mixing samarium oxide with a reactive metal like lanthanum, or heating it in a vacuum or inert atmosphere. Lanthanum, or sometimes calcium, will grab the oxygen, leaving behind samarium metal. Now, another method would be electrolysis. Samarium oxide can be converted to samarium chloride, and then molten samarium chloride is subjected to an electric current, which causes samarium metal to deposit at the cathode. Often the electrolysis is done in a melt with other salts like sodium chloride or calcium chloride to lower the melting point and improve the conductivity. The samarium metal then produced can be further purified. One clever trick takes advantage of samarium's relatively low boiling point. The mixture of samarium and other metal like lanthanum or europium can be heated under a vacuum so that samarium actually distills, boils off, and then condenses as a pure metal elsewhere, separating it from the higher boiling impurities. In the past, a mix of containing samarium was used in some early nuclear reactor control rods. As we will discuss later, samarium absorbs neutrons very well. That mix was a byproduct from extracting other elements and was named Lindsay Mix, after the company that made it. Now, today, samarium oxide is relatively inexpensive compared to some other rare earths because it's sometimes in surplus relative to demand. On a commercial scale, pure samarium oxide might cost on the order of only a few tens of dollars per kilogram, making it one of the more cheaper rare earth oxides. Its supply is more abundant than its current use. However, that could change if demand rises with new technologies. So let's dive into the applications. The most famous and commercially significant use of samarium is in making powerful permanent magnets, specifically samarium cobalt magnets. If you've ever heard of rare earth magnets, you probably know about neodymium magnets, which are the strongest type available. Samarium cobalt magnets come in as a close second in terms of strength, and they actually preceded neodymium magnets in development. These magnets are typically alloyed with formulas like these, meaning samarium and cobalt combined in certain ratios. Why add samarium to a magnet? Because samarium has a particular magnetic characteristics that, when combined with cobalt, result in a magnet that is extremely strong and also very stable under harsh conditions. Samarium cobalt magnets were first developed in the 1960s and 70s, and they revolutionized many technologies by allowing a strong magnetic field in compact sizes. They can be up to 10,000 times more magnetic than plain iron. One of their standout features is resistance and demagnetization. They hold their magnetic field even if they are heated to a high temperature, or if they are in a tough environment. Now, in fact, samarium cobalt magnets can operate at temperatures above 700 degrees Celsius or 1292 degrees Fahrenheit without losing their magnetism, whereas the otherwise strong neodymium magnets start to weaken around 300 to 400 degrees Celsius and even permanently demagnetize if overheated beyond their limit. Samarium's contribution is key to that high temperature performance. So, how does this relate to wind turbines? Well, wind turbines use generators that often rely on permanent magnets to convert the spinning of the blades into electricity. In modern wind turbine designs, especially the large direct drive turbines, which avoid using a gearbox, strong permanent magnets are at the heart of the generator. Many turbines use neodymium iron boron magnets because of their tremendous strength. However, these magnets have a downside. In very high temperature or corrosive environments, they can degrade. This is where samarium cobalt magnets shine. In extreme environments, for example offshore wind farms where turbines are exposed to salt spray from the sea and where maintenance is difficult, samarium cobalt magnets are valued because they won't corrode as easily and they won't lose magnetism if the generator runs hot. They are literally more rugged magnets. Some cutting-edge turbine designs and special applications use samarium cobalt magnets to ensure reliability. Even when neodymium magnets are used, sometimes samarium or other rare earths like dysprosium might be added in small amounts to improve temperature stability. So we can literally say that samarium is crucial for windmills. Samarium cobalt magnets aren't in every turbine, but they are an essential option in the toolbox for engineers, especially for turbines facing rough conditions. Now, beyond wind turbines, samarium cobalt magnets have many other uses. They are found in electric motors and generators of various kinds. For example, some electric vehicles and hybrid cars might use samarium cobalt magnets in their motors if high temperature tolerance is needed. Though many use neodymium magnets with special coatings or additives, it depends on the design. Now, samarium magnets also show up in aerospace and defense applications. Think of things like jet fighter engines or missile systems where temperatures can soar and you absolutely cannot have a magnet fail. The high stability of samarium cobalt magnets under extreme conditions make them nearly irreplaceable for certain military technologies. They've also been used in electronics. Small high-end headphones and speakers have used samarium cobalt magnets to get strong sound in compact size. Even some electric guitar pickups, the device that turns string vibrations into electrical signals, have been made with samarium cobalt magnets to reduce noise and improve tone. There's even a product literally called samarium cobalt noiseless pickups for guitars. Samarium's usefulness extends beyond magnets. One important area is as a chemical reagent and catalyst. Earlier we mentioned samarium 2 iodide, a compound where samarium is in the +2 state. This substance, usually appearing as a dark green solution in the lab, is famous among organic chemists. It's sometimes nicknamed Kagan's reagent, after the chemist who popularized its use. Samarium 2 iodide is a powerful reducing agent, meaning it can donate electrons to other molecules and thereby help form or break chemical bonds. It's used in a variety of specialized chemical reactions. For instance, to stitch carbon chains together or to remove certain hard-to-break groups in a molecule. Now, this makes it valuable into synthesizing complex pharmaceuticals and natural products. In simpler terms, samarium helps chemists build complicated molecules by acting as a helpful breaking and connecting agent in the lab. While this is not something most people encounter, it's a behind-the-scenes role that samarium plays in the development of new chemicals and medicines. Besides samarium 2 iodide, other samarium compounds also serve as catalysts. Samarium oxide and samarium triflate, samarium with some organic sulfonate groups attached, have been used to accelerate reactions. Now, for example, samarium oxides are involved in catalysts that help decompose plastics or harmful pollutants like PCBs. And samarium triflate can catalyze certain organic reactions, like a variant of the Fiedel-Crafts reaction, which is used to form carbon-carbon bonds in making chemicals. These applications leverage samarium's ability to interact with other chemicals and speed up the transformations. Samarium also finds its way into materials for glass and ceramics. If you add a bit of samarium oxide to glass, the glass can absorb infrared light more effectively. This can be useful for making safety goggles or optical filters that block IR radiation, for instance in protective eyewear for certain industrial processes. Samarium-doped glass has even been used for decorative purposes, imparting a yellow or orange tint because samarium can give glass a beautiful coloration and fluorescence under certain lights. Moreover, a tiny amount of samarium is often present in mischmetal, which is a natural mix of rare earth metals used in making flints for lighters. Those little sparks when you strike a lighter, they actually come from mischmetal alloy, mostly cerium, that includes about 1% samarium. So samarium has also a small role in something as everyday as a lighter flame. Moving on to a very different field, nuclear technology. We find samarium playing a critical role there. Certain isotopes of samarium are exceptionally good at absorbing neutrons. The standout isotope is samarium-149, which is a stable isotope that occurs naturally. Samarium in nature is a mix of isotopes, and samarium-149 is one of them. Samarium-149 has the highest known ability to capture thermal neutrons of any stable element. In nuclear engineering terms, it has a gigantic cross-section for neutron capture. This property is harnessed in nuclear reactors by using samarium in control rods or burnable poison rods. The advantage of samarium is that when samarium-149 absorbs a neutron, it becomes samarium-150 or other isotopes of samarium, many of which are also good neutron absorbers. In essence, samarium remains effective as a neutron absorber even as it changes isotopic makeup. It doesn't burn out quickly. This stability of absorption means that the reactor control characteristics stay predictable. In fact, samarium plays a role not just by intentional design, but also as a byproduct of reactor operation. Samarium-149 is formed in reactors as a fission product. When uranium fuel splits, among myriad fragments are various rare earths, including promethium that decays to samarium-149. Now, over time, Samarium-149 builds up in the fuel and eats neutrons, which can affect the reactor's performance. This phenomenon is known as the samarium poisoning, similar to a better-known xenon poisoning from xenon-135. Engineers have to account for the buildup of samarium when calculating how a reactor behaves over time, especially after shutdown when samarium concentration peaks. So, samarium is both a tool and a factor to consider in nuclear power. To put it simply, samarium helps to control nuclear reactions. It can be purposely added to keep the reactor's neutron population in check, contributing to a safe operation of the nuclear plant. Now, last week we talked about lutetium, which is a lifesaver. But is this rare earth element samarium also a lifesaver? Now, like lutetium, samarium even touches the medical field. A radioactive isotope called Samarium-153 is used in medicine to treat certain types of cancers. Samarium-153 can be incorporated into a pharmaceutical compound that is injected into the patient. One such drug is known by the trade name Codramate. Now, the next story sounds pretty similar to last week. Samarium-153 emits beta particles and a little bit of gamma radiation that can kill the cancer cells. The clever part is that the samarium is linked to a molecule that targets bone tissue, especially areas where bone cancers or metastasis, cancer spread, are growing. So, when injected, the compound travels and attaches to the bone cancer sites, and the radiation form Samarium-153 delivers a local zap to the tumor, helping to relieve the pain and reduce the cancer. Now, does that sound familiar to last week? Now, this is a form of targeted radiotherapy. It's often used in treating painful bone metastasis in diseases like prostate cancer or breast cancer, to give patients relief when tumors have spread to the skeleton. Now, our exploration wouldn't be complete without the mentioning of some emerging, fascinating niche applications of samarium. One area is the field of quantum materials and electronics. A compound of samarium, samarium hexaboride, has gained attention as what's called a topological insulator, a material that conducts electricity on its surface but not in its interior, with potential applications in quantum computing and advanced electronics. Researchers study samarium hexaboride to understand these exotic states of matter. Samarium is also being looked at in advanced batteries and fuel cells. For instance, samarium is used along with other rare earths in alloys for nickel metal hydride batteries, the kind that were common in earlier hybrid cars and rechargeable AA batteries. In these batteries, a mischmetal alloy containing lanthanum, cerium, neodymium, and praseodymium, and a bit of samarium serves as a sponge that absorbs the hydrogen. As the world moved to lithium-ion batteries, nickel metal hydride is a bit less prominent than it used to be, but it's still used in some applications, and samarium's presence in the alloy contributes to the battery's performance. In the realm of sustainable technology, beyond wind turbines, samarium is being explored in catalysts for hydrogen production. For example, samarium oxides combined with cobalt have been tested in processes to generate hydrogen fuel from reactions like methane reforming. Samarium's job in those catalysts can be to stabilize certain phases or assist in the reaction mechanism, thereby improving efficiency of producing clean hydrogen fuel. Another unusual application of samarium is in the study of Earth and planetary science. Geologists use a technique called samarium neodymium dating to determine the ages of rocks and meteorites. This works because one isotope, samarium-147, very slowly decays to neodymium-143 over geological time, with a half-life of about 106 billion years. Now, by measuring the ratios of samarium to neodymium isotopes in a sample, scientists can learn about the timing of events in early solar system and the formation of rocks, so samarium indirectly helps us to tell the age of some of the oldest objects in our solar system. Samarium is another example of how a little-known element can be vitally important. From the historical naming to its modern, indispensable applications, samarium's story is a fascinating intersection of science, history, and technology. The next time you see a wind turbine on the horizon or use a device that contains a tiny super strong magnet, you might think of samarium. the rare earth metal that quietly making big things happen. This unsung hero of the periodic table proves that even the most unassuming element can have a crucial impact on our lives, driving innovation and helping build a more sustainable future. Now, if you think I missed anything, leave it in the comments, and if you want to see another lanthanide, make sure to watch this video about lanthanum next.